So let's continue our examination of what happens to objects when we apply force to our solid object. So we're going to examine tensile stress, compressive stress, and shear stress. And we're also going to mention and talk about bulk modulus. So let's begin with tensile stress. Let's suppose we have a certain column that is hanging from the ceiling as shown, and the length of the column is given by the following variable L0, which is given in meters. Now let's suppose we apply a force onto our column, and the force points in the following direction given with the blue capital F. Now, the change in our object's displacement, the amount our object stretches, is given by change in L. This is known as the elongation distance of our object when the force is applied to our object. And the force is known as tensile force. Now, if we know the cross-sectional area of the column, which is given by A, we can calculate what the change in L is, what the elongation distance of our object is. That's given by this formula. The change in L of the object is equal to the product of 1 over Young's modulus, which depends on the composition of the object. For example, a wooden object and a steel object will have different quantities of E. So we take the product of 1 over Young's modulus and force divided by area, which is simply the tensile stress, multiplied by our initial distance of the object, our initial length of the object, L0. So notice when we apply our tensile force onto our object and we apply the force at this position, the force is felt throughout the entire object, and that means tensile stress exists throughout the entire object. In fact, if the tensile stress is high enough, that object can fracture, as we'll see in a future lecture. Now, what about compressive stresses? What exactly is a compressive stress? Well, in many different ways, compressive stresses are simply opposite of tensile stress, in the sense that instead of pulling on our column, we push down on the column. So let's suppose we have the following column resting vertically upward along the ground. So the length of our column is L0. Now let's suppose we apply a compressive force shown here onto our column. Our column displaces or compresses a certain distance change in L, and the cross section of the column is given by A. Well, to find the change in L, we can use the following equation, the same equation, to solve for that distance, for that compression distance. The amount our object compresses in meters is equal to 1 over E, where once again E is the object's Young's modulus. Force divided by area is no longer tensile strength, but now it's compressive stress. And this quantity remains the same. It's our L0, the original length of the column. Now, in the same way that tensile stress exists throughout the entire object and not just at this point, so does compressive stress exist throughout the entire object. Now let's talk about shear stress. So let's suppose we take a book that is resting flat on the ground. The shape of that book is of a rectangle. Now if we take our hand and we apply a force onto the top surface area of that book will experience shear stress. So let's suppose we had a book, we applied a force, and the force was parallel to the ground. The book's shape will slightly shift into this direction, and the change in L, the horizontal distance this corner of our book travels, is the change in L that we spoke about earlier. So this is the change in L for shear stress. Now the area is given by taking the surface area of the top or the bottom surface of our face. And the height after the object experiences shear stress is given by L0. It's the height of our object. So once again, an object under shear stress has equal and opposite forces applied to opposite faces, as shown with this force. And we can use a similar equation, except we replace our E, Young's modulus, with shear modulus, given with capital G. So, the change in L is equal to the product of 1 over G, shear modulus, which depends on the type of object and the composition of the object, multiplied by force divided by area, which is now shear stress. So in this case, we had tensile stress, here we had compressive stress, and now we're looking at shear stress. And we multiplied by the height of the object, L naught, also given in meters. Now, once again, shear stress changes the shape of the object, but the dimensions of the object remain relatively unchanged. And notice that the area that we need to use, this A, is the surface area of the side that is parallel to the applied force. So this force and this side lie along the same plane. Now, let's look at another concept known as bulk modulus. So far, we spoke about Young's modulus, E, and we spoke about G, which is shear modulus. Now let's talk about a third type of modulus known as bulk modulus. So if an object experiences inward forces from all sides, its volume will decrease. A very common example is taking an object and placing that object, submerging that object into a fluid. If we take a balloon and submerge it into a fluid, the volume of that balloon will decrease. So, here's our diagram. We take our object, we submerge it, and the fluid will create a pressure, a force that acts along all the faces of our box, in this case a square. And what happens is the volume will change, the volume will decrease. Now, if we want to find by how much our volume changes, we simply use an equation that is similar to this equation, except now instead of change in L, we have change in volume. And instead of a positive sign, we have a negative sign in front of 1 over B, where B is our bulk modulus. Now, the negative simply implies that our volume of the object decreases. So we multiplied by the force divided by area and multiplied that by our initial volume of our object. Now, force divided by area is also known as pressure. So we can replace force divided by area with change in pressure. So the change in volume of the object is equal to negative of the product of the change in pressure and the initial volume, and divide that by the bulk modulus of our object that we are using.